Hello. Intro to assembly for everyone. That's you. I make Game Boy games in assembly, and I want you to make Game Boy games in assembly. I don't want you to be afraid of assembly. I think assembly is awesome. I think it's awesome especially for non-programmers. Who am I? No time for introductions, so it's a quick presentation. Counting in decimal is what we're used to doing. We have 10 digits, and we count like this, 3, 4, 5, 6, 7, 8, 9, and then we have a problem. We run out of digits, right? So we add one, and we say that one is going to be worth 10 of the previous ones, and then we can go all the way up to 99, and we have the same problem again. And then we solve it the same way. We add another digit, we say this digit is worth 10 of the previous column, right? Counting in decimal is easy, it's intuitive, we do it all the time. Counting in binary, this is a crash course in binary. Counting in binary is exactly the same, it's just we only have 2 digits, so we encounter this problem immediately and often, right? 1, oh. Okay, add a column is worth 2 of the first column, 3, right? We gotta add another column, it's worth 2 of the previous column, that's 4, then 8, 16, 32, 64, and so it goes. Each of these digits is called a bit. This is what a bit is, and 8 of them together is a byte. And with 1 byte, you can count from 0 to 255. With 2 bytes, you can count like way higher, and 16 bits, 2 bytes is another important quantity for us. By convention, we write out all the bits in a byte, even if we don't need them yet. That's why binary looks all 0, 0, 1, 0, 1, 0, 1, 0, 0, 0. Let's enough talk about binary for now, though. We're going to talk about the CPU, in particular the Game Boy CPU, but like this generalizes reasonably well to other CPUs. CPU is the brain of the computer. It can execute instructions. The CPU has a bunch of hands, which are called registers, that it uses to manipulate values. These are a cheap, fast memory located near the CPU. On the Game Boy, these registers are called, they have names, A, B, C, D, E, H, and L. And these are not an abstraction. You can touch them with your finger. They're there on the computer. So it's like if you had a bunch of buckets and you named the buckets, that would be exactly what this is doing. They're 8-bit registers. So each of these hands, each of these many tentacles, can hold one 8-bit value. So now a CPU executes instructions. And here are some instructions, 2 instructions, real quick. Add. The CPU knows how to add 2 bytes. It needs to be holding the bytes in its registers. So you have a value in register A, and you have a value in register B, and then you can add A, B, and it will add those 2 values and write the result back into register A, okay? Compare is another instruction. We write CP for compare, and compare lets us take 2 registers and compare their values. If they're equal, if the values are equal, the CPU raises a flag called the Z flag. And we're going to need this later. So far we've got add AB, and we've got compare AB. Before learning the next instruction, I'm going to talk about memory, because you might not know what memory is. Memory is a list of bytes, okay? That's all it is. It's an addressable list of bytes. So each of the bytes in the list that is memory has an address, like a phone number. Even more importantly, the Game Boy's memory is random access memory, or we sometimes say RAM, and random access memory is more like a telephone than an apartment building. In an apartment building, to get to apartment 527, you've got to go up 5 floors and then down to the end of the hall. The further away the address is, the more time it takes to get there. That would suck if you were using a computer and you had to sequentially go through memory to get to an address. So instead, it's more like a telephone. When you phone your friend picks up the phone immediately. No matter what phone number you call, they answer immediately. Boom. That's what is meant by random access. The address space, an address space is like all of the possible addresses that a CPU can know about. Different CPUs have different kinds of address spaces. The Game Boy has all kinds of little bits, right? It has like internal RAM, and it has the cartridge. And a cartridge, the Game Boy cartridge, it's just a list of bytes, right? And the Game Boy internally is just a list of bytes. And they all have addresses that are inside of that big address space. An address space has limits. So a phone number is 7 digits, which you can use to represent 10 million phone numbers, unique phone numbers, right? But as I mentioned earlier, just a single byte, 8 bits, can only go up to 255, which is just not enough addresses to represent a useful address space. So we use 2 bytes, which is 16 bits. But I mentioned earlier that the registers are 8-bit registers, which means that the 16-bit addresses are too big. The CPU can't hold on to them. So in the Game Boy's case, what they do is you can combine 2 of your 8-bit registers into a single 16-bit register for manipulating addresses, right? And the 16-bit registers are BC, DE, and HL. This probably seems like a lot. This is a lot. I'm going very quickly, but I'm introducing your tools, right? So you have buckets named A, B, C, D, E, H, L, and then you have these bigger double-handed buckets called BC, DE, and HL. So the last thing to mention about memory is that we can give addresses human-readable names in our code. The CPU doesn't know about this stuff, but it's just for us so we can read the code. So here you can see player X refers to a memory address, and there's a value there. So the CPU can get values out of memory using its tentacles by using the load instruction. The CPU loads and stores the values that it needs to work with into its little hands, the registers, using the load instruction. So here's an example of the load instruction here. Player X is a 16-bit address, right? So that's like a phone number that you're going to use to call up the place where the player X is. HL is one of these two-handed 16-bit registers, and load is an instruction. So when the CPU sees this, it's going to take that address, and it's going to put it into its 2HL hand, right, into its 16-bit register. And then to get the value, right, HL is holding the address. To get the value, you got to dial that phone number. You got to call it up. That's why we use these square brackets, because they look like 90s telephone receivers, right? Business. We're putting together, we're calling HL, and we're getting the value. So now load A, HL, is how we get the value, player X, into a hand, right? So that we can add it to something or whatever, operate on it. One more time. Player X is an address. HL is two hands. Then we dial up HL on the telephone. We get the value out. We load it into A. We're building to something. We're going to do something. But this is already huge because now, just with that one instruction, you have everything that you need to start updating values in memory, loading values out of memory, adding them together, and then writing them back to memory. So I'm going to write a little program that updates the player's X coordinate, because that's something we do in video games. So here's this. You've seen this before. Player X into HL, call up HL, get the value. Do the same thing again, but this time we're loading the velocity, the change in X, into B, which is another register, right? So now we're really using all of our tentacles. And then add AB, and, I skipped a slide there. Add AB, right? Adds them together, and recall, it stores the result back into A. And then you're going to load that player X address again into HL, and this time we're flipping the script. You can see that the telephone call to HL is on the other side. We're writing now. We're writing back into the player X the updated value, right? So, and that's all a video game is, right? Like you load some values from memory, you update them, you write them back to memory. Farming, exploring, skeletons, red keys, locked doors, etc. They're all just values in memory, and you update them. We have the instructions we need here for updating values. So you can make an entity move around, right? We've updated an X value, do that in a loop. You can have a byte that says whether or not the player has a key. You can plot the growth of a plant as the number goes up. And the missing piece for video games is loops. Video games don't just go once and then stop. They loop over and over and over. So next, we will learn how to loop jumps. So loops are achieved by laying down a label in your code. So you write something like .main. That's just a label. And then later on in the code, you'll use the jump instruction, JP, to jump back. So normally execution goes one instruction at a time, but when you hit a jump, you can jump to somewhere else in the code. So here, for example, this loops forever. Main, do some stuff, jump main, do some stuff, jump main. If you put the code that we wrote before to update the player's position into a loop like this, then your player would rocket across the screen as fast as they can go. Right? Main, do all the stuff that we need to do to update player X, and then jump to main. So conditional jumps are very important. What if we want to restart the game, but only if the player's HP is 0? If the player's HP is higher than 0, we don't want to restart the game. We have a label somewhere called restart. Jumping to restart would just always jump back to restart. So what we're going to do is condition the jump. So jump Z to restart. Remember the Z flag? I mentioned that earlier. When you do a comparison, when you compare A to B, that action, if they're equal, if A and B are equal, the Z flag gets raised, right? And if the Z flag is up and you jump Z, then you'll jump back to restart. If it's not, if the Z flag is not raised because the values were not equal, you won't jump. So you always have to sort of do a little bit of a comparison or some math ahead of a conditional jump in order to prime the flags that it's going to be conditioned on. So if we want to restart, if the player's HP is 0, we load HP. You've seen this before. Load the value of HP into A. And then we compare A to 0, and then conditionally we jump, right? So this is 4 instructions you've learned, right? And you can load, compare, add, jump. We can add, subtract. Is obviously, if you can add, you can subtract. That should be intuitive. Increment and decrement, just add 1. It turns out to be like weirdly useful to have a specific instruction just for adding 1 or subtracting 1. And honestly, 80% of all the code I write on a day-to-day basis is just these 7 instructions. So like compare that to trying to learn Java or C or something. Like what's a class? What's a inheritance hierarchy? What are all these different loop constructs? You know, like a while loop and a for loop. And when would I do while instead of a do for? What's this while true and all this stuff, right? Here you just got the 7 instructions. You could learn this in an afternoon and then you can get going, right? And so I'm going to be, after the talk, I'm going to be over there with a computer open with an empty Game Boy program. And I want someone, hopefully one of you at least, I realize this is a little esoteric, but if someone comes in and enjoys with me doing a little bit of assembly, that would truly make my day. So I'm going to just touch on rendering. I don't think I'm going to be able to get into it because I've got 1 minute left. There is, so one more missing piece to the puzzle, right? Which is like, okay, we can update values in memory, but a video game isn't just 2 lists of bytes, right? I mean, it is just 2 lists of bytes. But you need to be able to show things to the player, and you need to be able to read, right? And as I said before, the only thing the CPU does is read data, perform instructions, and write data. So is there like a render instruction, maybe, like RND or something? No. The Game Boy hardware is wired up in such a way that there are certain bytes in memory that are the screen. And then there are other bytes that are controlled by the buttons. So when the player holds down the A button, like there's a bit that literally gets flipped, and you just read that byte, and then you know what buttons are held down. If you want to render things, that's exactly it. You write to those bytes. So really it is just a couple of lists. We're out of time, so we're not going to take the plunge. So I'm going to skip. Keep going? I'm going to keep going? Okay, all right. So what I was going to do was I was actually going to, I had some slides set up here as an overview. So the Game Boy's screen is controlled by an area of memory called video RAM, right? So you've got memory. It's divided up into little areas. Some of the areas in the address space are like the cartridge, and some of them are the working RAM where you keep all your values. One of them is the video RAM, and it's just this big chunk of RAM. It's divided into 2 parts. The tile data, which is a database. The Game Boy is a piece of hardware that is specifically designed to make making games easy for you. So it's got this stuff set up. It's got a database of tiles, and then it's got the tile map data where you reference those tiles. And I want to make something clear before I go any further here. Your game is on the cartridge. It's a list of bytes that is your game. It's on the cartridge. The VRAM is on the Game Boy. So we have to copy all of the data into the Game Boy, right? And then I'm going to define a tile here. A tile in the Game Boy, the atom of rendering in a Game Boy is not a pixel. You can't draw pixels to the screen. You can draw a tile, an 8 by 8 pixel image. And the tiles, like if you think of it, the Game Boy's got only 4 colors. 4 in binary, right? You can represent 4 values with 2 bits. So it's 2 bits per pixel. 8 by 8 is 64 bits. And then 2 bits per pixel, 128 bits per image. That's 16 bytes. So one tile is 16 bytes. I was going to do, so this is the part that I'm going to skip because I was going to do a visualization like this with some images, but then I realized I could use my laptop here, right? So this is an emulator running, I crashed. Oh, it's not my software that crashed, it's the emulator that crashed. Okay, hold on a sec. Oh, this is like bad press for poor Emulicious here. I swear to God, this is a great emulator. You should use Emulicious, but like, just don't close your laptop. Emulicious. It's because it's written in Java instead of assembly. And then, where am I now? Hello world. All right, okay. We'll get rid of this thing. And okay, so this emulator is a developer emulator, and it's visualizing the parts of the VRAM for us. So over here, can you see my little cursor? Where is it? I can't see it. Over there, great. This is the tile data. Each of these little slots is a tile, and it starts with the Nintendo logo and some trademark information in there already, preloaded for your delight. And then this part is the tile map. This is like the visible part of the screen. Each of these little squares represents 16 bytes, right? It's like the instructions on how to draw all the pixels in your little image. And then each one of these is just a reference to one of these pixels, one of these tiles. So like you can see the one that I'm looking over there, it says tile index. See that? Tile index 256. And if you look in the list of tiles down here, you'll find tile index 256. That's what it's going to render to the screen. So it's the play of these two, the database of tiles and then the level, the graphics. So I've prepared some addresses. So VRAM tile data is the address of the beginning of that tile data in VRAM, and VRAM map data is another address. These are just 16-bit addresses, right? You can see the address there. And then I've prepared a white tile that's just 16 bytes that are all 0, and a black tile, right? 16 bytes that are all 1. And I'm going to copy. So this is like you saw this earlier. So I'm going to load HL with like the destination, which is the tile data. And then I'm going to load DE, which is another of my like double-handed 16-bit registers. I'm going to load it with the black tile. That's another address, right? Black tile is just an address. It's where I chose to store that data. And then what I'm going to do is I'm going to copy the black tile into the VRAM, and you will see it magically appear in the Game Boy. So I'm going to need to loop. I'm going to need to make a loop, copy loop, I'll call it. And the loop is going to go until it's done. And it's going to go 16 times because there's 16 bytes in a tile. So I'm going to copy 16 bytes, right? And all of this you've seen before. These are just the instructions that you already know. I'm loading A with the black tile, which is in DE. So I'm calling up DE and I'm saying, hey, give me the first byte of the black tile. And then I'm going to load HL with A. I'm saying, hey, HL, I got the HL on the other phone, and I'm like, hey, you know, the value of that first byte, it's 1. And then I'm going to increment HL, and I'm going to increment DE. So I'm now pointing to the next byte, right? And I'm going to do this 16 times. And I'm going to count through 16 times by decrementing B, right? B has this 16. And then I'm going to check, is it 0? When I decremented B, did it become 0? And if it did, then I'm done, right? I've copied all of the bytes. And if it didn't, then I'm going to jump back to the copy loop, right? And that, of course, live coding is always a mistake. There it is. There it is. Right there. And you can see that it changed what is being rendered on the Game Boy screen, because all of these, like the map that we're rendering right now is all zeros. It's all referring to tile number 256, and I changed tile number 256. Maybe that was a silly idea. So like maybe I should have loaded black tile into VRAM plus 16, which is like the next tile over. Oops. And then when I come back in, there, yeah. So now I've got a blank tile that I'm going to keep there. There's a little bit of garbage. You can see there's a little bit of garbage. Uninitialized RAM, always zero out your RAM. And then the tile is rendered there. So that's it. That's the presentation. I'll skip to the part where questions. No time for questions. Come see me later. And these are the Googleables. You can Google these. And so if you are the one person who was like, oh yeah, this really speaks to me, I want to do this. These are the things you should Google. The assembly line podcast in particular, really entertaining, very nice, and then the Pandocs at the end. Thank you.